Hello, in the last lecture we discussed the kinematic approximation for the locus of the loaded tip of a cantilever beam undergoing large displacements. Today we are going to talk about elastostatic approximation, and that leads to something useful later on. So, we are looking at elastostatic approximation of the locus of the loaded tip of a cantilever beam. So, we had seen that there was this eureka moment for Burns and Crossley when they noticed that there is a circle here for the locus. So, all these collection of data points were obtained by applying on a cantilever beam load that is inclined, that means it has a transverse component as well as axial component, and they all happen to be in this tiny sliver if we neglect some of these things that happen when you apply very large axial load or very large axial load that is tensile here and compressive here. But more or less if you were to notice, there is a dashed line there, dashed curve, that is a circle approximation, that is a kinematic approximation. How is that useful? Because as you can see from here to about there, it is very close to the circle barring a few compressive axial loads, and if you go further it is deviating a little bit, but more or less you can approximate the motion of a cantilever beam tip with a crank that is a little shorter, that is here we have about there. If I put a center, then I can put a crank that, I think I should change the color here. So, if I put the color, I want, let us say blue color, yeah. If I put a crank there, okay, which rotates about this point as if it is fixed there, the motion of the crank, rigid crank, will be similar to the motion of the cantilever beam with load that can come from the transverse side or the axial side. Axial can be that way as well as this way. If we do all that, we get that sliver of thing as we saw there. It was something like this, which we can approximate, all of the approximated with a single circular arc. That is the kinematic approximation. That means that we have the contribution of Burns and Crossley, who said that we can approximate this with a pin joint there, and we have a crank that traces this. If there were to be only transverse load, you can see how good the approximation is up to about this point, all of this, that is a lot of angle, maybe close to 60 or so, and that much beams do not bend often in compliant mechanisms. That is, with this load here, the beam would be bending something like this. That much of deformation, in fact it will not be 0 there, it will be something like this with the 0 slope there. That much deformation is actually not quite common in compliant mechanisms. So, it is a good approximation if you were to replace this cantilever beam with a rigid crank whose length, they said, is 5/6 of the length, that is from here to here, the crank length I should say 5/6 times L, and you have to move that fixed connection by 1/6 L or L by 6. If you do that and put a rigid crank, then you get a very good approximation for the tip of the cantilever beam, and that is exactly what they said in 1968, okay, 5/6. Now, we also discussed, can we solve problems like this? Our answer in the last lecture was yes. That is, somebody asks us to generate a function where psi is a function of theta. We can do that because all we have to do is, over here we reduce this beam length by 1/6 and add a rigid body here and say that this is where I extend this fixed one, this is all fixed now. Okay. Now, I have this new length which is 5/6 of the original length. I have rigid body linkage, and for that I know how to do this function generation synthesis, meaning if somebody asks us to generate a function psi of theta which is given or this is prescribed or it is desired, if we have that, we can find this length L, this length let us call it L2, L3 and this length from here to here, okay, because that is a new pin joint there over there. So, L0, if I have these, I can find L0, L2, L3 and my 5 by 6 L, let us call that L1 or something. Okay. So, all of these things we can find so that this function is generated. After we do everything here, then we replace this particular rigid body with an elastic segment that is 1 by 6th more in length. If we do that, then we get a compliant mechanism that has two rigid bodies and an elastic segment and would have designed it. Okay, that is the significance of this kinematic approximation, because in kinematics we only care about how this is moving, and we know that even if to be a cantilever beam, it would only move along a circular arc very close, an approximation, but very close approximation. Okay. And when a linkage is like this, the load at this point can come in any direction. It is a pin joint, there will not be any movement as yet, but the force can come in any which way, right. And that is why we had considered on the cantilever beam loads both transverse and axial, so that the inclined load in lot of different directions. All of those, if you approximate this with 5 by 6 L, Burns and Crossley said that you will be very close to what the cantilever beam would be doing if you would replace the cantilever beam with this rigid body. So, that is the kinematic approximation. Now, we also ask this question, when you make this equivalent rigid body model, that is if I have a cantilever beam, okay, which is fixed at one end, other end it is attached to some rigid body, whatever it is. So, that rigid body at this joint is going to create loads in different directions. We do not know which way the load can come in any direction. It does not matter whichever direction the load may come, we know that we can approximate this rigid body with that elastic body with a rigid body where we put that joint, right. That is the equivalent rigid body model. So, as far as the motion of this is concerned, right, it will be symmetric when the force is downwards, it will be a circular arc around this point and that length is 5 by 6 L. Okay, that is equivalent rigid body model. Then we can go back to rigid body linkage synthesis or analysis and work there, and then come back here and replace the rigid body with a longer cantilever beam. Okay. This works well for fixed and pinned elastic segment. Okay. Now, if you look at this, right. So, here is where we are showing all that crank, the black lines here are the crank directions and the red ones are the elastically deformed cantilever beam. The red ones, each of these here, these are all the beam deformations, and then we have this black ones, that is, you see these black ones, they are the crank rotations from here to here, and both of them are lying on this curve, and then of course they deviate. So, deviation starts to become apparent from this point onward, they are slightly deviating, and as the deflection becomes more, they deviate more from the circle. Okay. So, now if we see that kinematically this works very well, what about the torsion spring constant? Because if I have a cantilever beam, let us say I have a cantilever beam and I have a force here, I know that it deflects like this, and we know that this thing, if we have, let us say this deflects like that, this can approximate this circle there. If I replace that with a rigid body, okay, that is what we have been saying, that if I replace that with a rigid body now, it is going to move exactly like that, right. That is what we saw. For a large rotation they are coincident. Okay. But then a cantilever beam will offer some resistance to the application of the force. If I just put the rigid body like this, kinematically for function generation problems, that is this function that we took psi as a function of theta, it is perfectly alright, because there is no information of the force. But if I were to also consider the relation between force and the angle psi, that is I want to know how psi changes with f, not just psi as a function of theta, which is purely kinematics. If I say psi as a function of f, if that is what I want to know, then I have to get some notion of elastic model in my equivalent rigid body model. This is my equivalent rigid body model. Now, if I show just like this, that is if I just say that I have a crank of length 5/6, right, and apply a force, it is just going to rotate. We have to go to dynamics, right. It is not going to settle at some point like the cantilever beam would do, because this lacks elastic element. So, what we say is that we can imagine that since it is a crank, if I imagine that there is a torsional spring, okay, this is the torsion spring or rotational spring. Okay. Whenever we show a spring, we implicitly assume that it is linear, right. I mean, it need not be. In fact, compliant mechanisms are non-linear springs, but whenever we see, if I draw a spring like this, immediately I want to know what this K is, right. Similarly, if I show a torsion spring like this, I want to know what its kappa is. So, kappa is torsion spring constant. If it is linear, torsion spring constant. What do I mean by linear? If I were to move this, it is going to rotate, there will be a reaction moment here due to torsion spring. That reaction moment, if I call that m, that is going to be equal to kappa times this angle, let us call it psi rather than theta, let us call that psi. I am still in the eraser mode, let us call that psi. Okay. This is the moment, and this kappa is spring constant. When I multiply by this angle, I get the moment here, and that moment and this force F times that moment arm will be equilibrated. So, this will be in some kind of a static equilibrium where it turns like that. There will be F here, and then you have the momentum F L cosine psi, that will be equal to this moment m, which is given by kappa times psi. Okay. We assume that. Is it the case in this example is our question. That is the next question. What about the torsion spring constant? If I replace a cantilever beam with an equivalent rigid body that is a little shorter, and if I were to put a torsion spring over here, what is this kappa here? First of all, is it linear like this, meaning that at different points here, is this spring constant the same value? Does it remain constant? Okay. Because for each rotation, if I do, that is f some value, increase another value, as I increase the force, it is going to go from here to here to here, meaning the cantilever beam will bend like that, and then bend like this, and bend like this, and so forth. As it moves with increasing force, and each time between two increments, if I were to calculate this kappa, is that going to be the same or is it going to be different? That is what we would like to know. Okay. And that is what I have done here. So, here for various values of forces starting from 0 to about 6 newtons, we calculated that value kappa here. The units of kappa, Newton meter per radian, because if I multiply by angle, I should get Newton meter, that is a moment thing, right. And this is another Eureka moment, that it is almost constant. It is not exactly constant. To generate this, I have taken length of the cantilever to be 1 meter, and Young's modulus, I took that of steel, that is 210 gigapascal, and I have taken rectangular cross section, okay, that I will be B dq by 12, and I took this B and this D. B I took 5 centimeters and D I took 1 millimeter, and varied the force up to 6 newtons. Okay, that is 6 newtons. When we do that, this torsion spring constant ought to be almost constant. Well, it is not quite, right, it is not exactly constant, but almost constant. So, we can approximate the elastic nature of the cantilever beam now by introducing torsion spring constant. This kappa is not going up and down, it is going up and down a little bit, but relative to the 0 base that I have taken, it looks pretty much constant. If I take some average value in the middle, so average is always in the middle, if I were to take some thing like that, right, whatever value that is, then I would be approximating the elastic behavior also here in a convenient way, where this kappa is constant as the force increases. That is, I just said that as the force is increasing, when I do incremental steps, is the kappa the same, it turns out to be in fact very close to being constant. So, the torsion spring constant is almost constant. Okay. That Eureka moment, well, I mean, this is the MATLAB code that you can also try. Along with this lecture, there will be supplementary files where you can see we find the crank angle psi, that is, if I have a beam and when it deflects like this, I take the rigid body pivot over there. Okay, cantilever beam was fixed there, it will go like this. Now, I am joining this from here to here, that angle I am denoting by psi. Okay, that is I a tan 2 function gives you the right quadrant, WL and then 1 plus UL, the way UL was defined in that particular code. So, basically what we are saying is that I want to take this vertical thing, this horizontal thing, and that is what we have, this psi. Once you have psi, we can calculate the moment, assuming that here the load has both a transverse component as well as axial component, we can get the moment here, and then that kappa is obtained by dividing moment by the angle there, and then plotting kappa and how close it is to being constant, and we saw that it is close to being constant. And these inclined loads, so if I were to take some value 6 Newton that I showed there, right, each time I also take an axial force, which is that if I call this F, I would take n times F as axial force, n times F as axial force, that is, if there were to be transverse force F, there is n times F. Actually n, let me positive is that way, and n is negative, it becomes compressive axial force. Okay. So, n direction is this way, n times F. Okay. So, with various things applied here, each time doing equivalent crank, if I were to do, that was just for one force 0 to 6 newtons, no inclined load. Now, we have taken inclined load also, and then see that the spread here that you see again is not very much, that is like the sliver of the fixed tip, if you see how close it is to the circular arc, right. Similarly, the kappa here is also pretty much constant. Okay. Now, here is another one where we are taken more inclined loads, varying n from -1 to 1, meaning that as I am varying this force 0 to 6 newtons, I am changing force all the way from +1 to -1. Okay, that NF that we are taking, n varies from -1 to 1, compressive to tensile. If you sweep all that, it increases a little bit more, but again not deviating too much. And nice thing is that as force increases, the spread increases. That means that for lower forces, let us say I am applying only 3 newtons, meaning I am not deflecting the beam a whole lot, then I am closer to being constant than it is for larger forces. Okay, you can see the force here, the beam is deflecting all the way like this, right. So, it is deflecting, let me change the color. So, it is deflecting like this, that means that there is axial force and compressive axial force and tensile transverse force which is deflecting so much, and yet we see closeness to being constant. Okay. So, if we just see the spread again, when it is only compressive load -1 to 0 versus -1 to 1, the spread is increasing, but it is narrow enough to be approximated to be a constant kappa. So, kappa being constant is the main message here. Okay, that is the eureka moment, and that was the contribution of Howell and Midha. Professor Ashok Midha was a professor at that time Purdue University, and Larry Howell was his student. They observed this very nice thing, that this kappa is constant, and that is what I call elastostatic approximation. When Burns and Crossley did that in 1968 for kinematic approximation, and they said it 5/6 L, they said, well, not only that, this kappa that we have, okay, they used K. So, that let us call it kappa spring constant, that I can just fix it here, and if you close your eyes, whether I put a rigid body with a torsion spring or an elastic beam, this point here in response to the force that is applied here will not be able to make any difference. That is, if I present to you a model of a rigid body which is slightly shorter than the original elastic beam and put torsion spring constant and give it to you, you will not be able to tell the difference between this and the cantilever beam to begin with at all. That is, we have both kinematic and elastic approximation, or elastostatic I am emphasizing, where dynamics may change, static conditions you do not find the difference, and that is the nice thing about this. And this is the paper where they published in 1995, several years after Burns and Crossley, but they had this wonderful observation that this kappa is constant. Okay. And that is their thing. In fact, in this particular case, I put that they had given this expression also 2.25 times EI by L. We will come to how they arrived at this value, this particular formula for the torsion spring constant. Okay. When I put that 2.25 E and then I here, I took 5 centimeters and then 1 millimeter BD cube by 12. I got 1.9688, and that was very close. If you see, let us see, yeah, not here, but let us go back. If you see, it was very close. This is 2 Newton meter per radian, and it was there. Even if I change n all the way from -1 to 1, that is compressive axial completely to tensile axial, while the force was acting as much as 6 newtons, where it was deflecting a lot, it was very close. 1.98 will be somewhere just like that over there. That is what anybody would take if you were to make constant, and their formula agrees with the example data that we have taken here. And again, let us see the approximation. If you consider the locus of the cantilever kinematically, the reality is that it is not a circular arc, but you can take it and get away for most situations. In a similar manner, the elastic approximation of putting that torsion spring over there, torsion spring, right, that kappa being constant will be similar to this. It is a spread we saw, and now we say that that is constant. If you take, then we are okay for most of the situations. And Howell and Midha called that pseudo rigid body model. That is, you have a cantilever beam, that is a real cantilever beam, but you are approximating its behavior both in terms of kinematics as well as elastostatics by a rigid body and a torsion spring. Okay, this is again kappa. That is what they call pseudo rigid body. Pseudo is not real, it is a rigid body model for sure. They called it a pseudo rigid body model because you are replacing a cantilever beam with a rigid body which is fixed over there, and there is a torsion spring. So, this is the pseudo rigid body model. These days people use that PRB model, pseudo rigid body model, okay, that is built up based on two things, kinematic approximation and an elastostatic approximation. They did one more thing, they defined this gamma, which they call characteristic length factor. They chose a value of 0.85 rather than 5 over 6 that Burns and Crossley had used. 5 over 6 is 0.8333, right. So, 0.833, easy to correct, 0.8333, right. Instead they went for 0.85, right. Why did they change it? And they actually introduced later that thing also here. We will see how they did it, how they arrived at this formula and why they went for 0.85. Okay. So, what they did was they did very extensive calculation using elliptic integral solutions as well as finite element analysis, where they took a beam, okay, there is a cantilever beam of length L with some Young's modulus, cross section area and so forth, applied the force so that it has transverse component, axial component, both in terms of tensile as well as compressive for the NF here, just like what I said. They did that and then they fit circular arcs to the data. If you remember, I also showed this spread of these points of the locus. When they took that and they approximated with circular arc, because that was already known, and they tried to see what is the best circular arc radius and where should that be. That is, they tried to obtain this value gamma, what we call characteristic length factor, that is from here to here will be this gamma L, where gamma they took it as 0.85. In fact, what they found was different ranges of n as shown here. When n varies from 0.5 to 10, that is when n is tensile, the axial load is tensile, they gave something 0.84 minus 0.007. In fact, these are all approximations. In another slide I have the 6 decimal place accuracy they give for this fitted curves to find this characteristic length factor. And where would you fix it? From here to here will be basically 1 minus gamma times L. You move the fixed support to here, make it a pin joint support, put the torsion spring of spring constant given by that formula, and they said that depends on n value, when n can be varying, when n varies for each range of n, the first range, second range and third range, they gave a formula for gamma. Similarly, for this k theta, for this also, which goes over there, that is given by this one there, they are given some values, or of course range of n for this and range of n for this are different. Okay. It is all by fitting the curve, and in each case what they did was they approximated this with a circular radius, arc radius of gamma times L, where gamma is the characteristic factor, and this kappa. What they did was, when they get this spread of data, that is, if I take a cantilever beam, it is going to give some points like this, right, and we have seen that with in the earlier slides, they will be like this, right. So, now first thing they did was, if I were to approximate this with a rigid body crank somewhere there, okay, this is a rigid body crank of length in their notation gamma times L, where this is gamma is a characteristic factor. They try to find this gamma through fitting in such a way that the angle, if this were to go like this angle from here to here, let us say this, they try to maximize this angle. Okay. To what extent I can go in terms of rotating this crank, in other words bending this elastic beam, so that the error between the circular arc and the spread of data is minimized. So, they try to maximize this psi for given error. So, you may say error should be less than some epsilon. Okay. For that they try to maximize this rotation, and based on that they came up with these values of gamma, and at the same time they also came up with the values of kappa, because kappa again they would try to see, okay, if it goes there then the moment here has to be equal to kappa times the angle psi. The moment of course comes from, if I have the force, that component as well as this component, let us say you can take moment about this and you will put that there, that should be equal to k times psi, and that is how they did this curve fitting, so that they can get an approximation for these things. Okay. Again this is gamma k theta ei by L, they are putting the material property, cross section property, length L, and gamma is given by this. Now given a more detailed expression, they have put 841655 and then 0.0067807, so many decimal places based on their epsilon that they had chosen error. They fit that for different ranges, n varies from 0.5 to 10 and then minus 1.8316 to 0.5 and so forth. Okay. They have given different ranges for these values. You can get n, and then you can also get this k theta, for which from the book by Professor Larry Howell I have taken this image where this k theta, you can see there is n square, n cube, n to the 4, and you know all that, all the fitting that they have done to arrive at this, so that you can get something that approximates for certain angle. In fact, for each of the approximations they give to what extent you can assume that this will be accurate within the epsilon that you take. Error you predefine, within that error this kinematic approximation as well as elastic approximation will be accurate to given error, and that is how they have taken. And they have extended this pseudo body model not only for the cantilever beam, but also for the fixed beam. When I have fixed and fixed end, this is fixed here as well as here, you can approximate like this, and for many other situations which we will consider in the next lecture. Just to summarize now, Burns and Crossley found a very good approximation for the kinematics, and Howell-Midhas found a very good approximation for the elastostatics, and both of them put together leads to this pseudo rigid body model, which we will discuss in the next lecture in a little bit more detail. So, if you want to refer to something further, I have given the reference to the book by Larry Howell as well as this fundamental paper that was published in 1995, which is worth reading, where they explain the details of how they fitted the curve, lot of painstaking work after their initial observation that this torsion spring constant is indeed constant pretty much with very little error over a large range of rotation of the cantilever beam under inclined loads of all kinds, compressive, tensile, axial loads and transverse loads together will lead to this nice elastostatic approximation. Thank you.